Hey everyone, welcome back. It was great seeing some of your faces in the Google Meet. We'll continue those 1 hour block meetings once a week for the unseeable future right now. But just keep up the good work. Make sure you're watching these videos and staying on top of your schoolwork. Let's start with similar to what we did last class. I'll warm up with 4 problems. You can go ahead and pause this video and work through them, and then I'll put the answers up after you unpause. Okay, so for number 1, if it's a geometric sequence, you know that there needs to be a common ratio. And your trick when you're given, well, you always want to find the ratio and you always want to find the first term. Ratio, first term. Your trick when you're given 2 terms is to find the ratio is the difference in term number. So 2 and 5, that's a difference of 3. That becomes the index in your radical. So the cube root of the term on the right, which is 4, the term on the left, which is our 108, and then just reduce this down and you'll have your common ratio that you were multiplying by to go from 108 to 4. So this simplifies to the cube root of 1 over 27, which is a perfect cube of 1 over 3. Okay. First term, you need to go back to find term 0. So from 108, we need to multiply by 3 to go back to term 0. Our 108 times 3 gets us 324. So then our explicit rule would be a sub n equals 324 times 1/3 to the power of n minus 1. Okay. If you wanted to use term 0, just multiply by 3 2 times, and that would be 1/3 to the power of n. For number 2, the ratio was -2. Remember, when it's multiplying negative, or when it's going from negative, positive, like it was up here, you know your ratio is going to need to be negative. So -2, and then our first term here was negative 0.125 or negative 1/8. So our rule would have been a sub n equals 0.125 -2 to the power of n minus 1. Okay, last 2, these were series. Number 3 was asking for the partial sum of the first 7 terms in this sequence. And then number 4, finding the sum from 40 all the way down to -210. So for number 3, all of these I would just put into sigma notation and punch into your calculator. Remember to get there on Desmos, function, miscellaneous. There's your sigma. So our starting at 1, going up to 7 terms. And then the rule here was 14. This was a geometric series. It was tripling 3 to the power of n minus 1. And just punch that in on Desmos. Make sure you're careful with sets of parentheses. So 14 times 3 to the power of n minus 1. Close, and we would get a partial sum of 15,302 for the first 7 terms. Number 4, hopefully we all noticed that this was an arithmetic series. The difference was -10, -10, -10. That's going to help you write your rule. It's also going to help you find how many terms are in this series, because when we go to write this in sigma notation, 1 for our lower limit, we don't know what that upper limit is. We need to know what term number 210 is, and you can just use a sub n equals d times n plus a sub 0. This explicit rule for an arithmetic sequence to solve for that term number n. So we're going to plug in -210. The common difference is -10. We're solving for n, and then term 0 would be back at 50. Okay. So subtract 50 over, we get -260 equals -10n. which means there's 26 terms in this series. And you could also get that, guys, by counting. You could count on your hand if you want, but that might take a little bit more work because you're going from 40 all the way to negative 210. 26 is our upper limit. And then our rule is, let's just do negative 10n plus 50. Punch that in on Desmos. I'll let you guys do that on your own. You would get negative 2,210 for this series. Negative 2,210. Okay, great job for the warm-up. If you have questions on this, I can answer them during our office hours next week. Let's move on to our last lesson for this unit, which is infinite geometric series. So I'll let you guys get this written down. And we're going to start, you're going to want two graphs. So you can download these from Google if you want and just crop them and then paste them into your notes. You could also just use the graph paper option on Notability. Okay, but let's start with two infinite geometric series. Remember, if they're infinite, we're going to need that ... at the end. These are going on forever. So sum of n terms for 4 plus 2 plus 1 plus a half plus a quarter plus an eighth, going on forever. And let's do S sub n, the sum for 2, 4, 8, 16, going on forever. All right, so hopefully we notice these are both infinite series. They go on forever. And then they're geometric because the ratio in this first series was 1/2. And then the ratio in the second series was 2. So one, every term's being cut in half. The other, every term's being doubled. And what we're going to do here is we're going to make a table. And in that table, we're going to have n, which represents the number of terms. And then the sum for whatever the sum is for that given number of terms. So let's make a table for both of these over here. N and sum. When you guys are ready, we're going to find the sum for 4, 5, 6. The first couple of terms in each of these series. Okay, so how this works is for this first example, with one term, well, there's only one sum. It's that number 4. Now, when we have two terms, that's the sum of these first two values. So 4 and 2 gets us 6. And when you add another term, there's three terms. 4 plus 2 plus 1 gets us 7. And we're just going to fill in this table. Now we're adding a half. Now we're adding a quarter. Now we're adding an eighth. And we'll just stop right there. 1/8 is 0.125, so 0.875. Okay, over here, one term would be a sum of 2. Two terms would be a sum of 6. 3 would be a sum of 14, 30. And we're just going to stop right there because we'll be off our graph after 14 anyways. Okay, so let's go ahead and sketch the shape of this graph and see what we notice. For this first example, starting at 0, then when we add one term, we're at 4. Add another term, 6, 7, 7.5, 7.25, and we're getting really, really close to this value of 8 is what we should notice if we continue this table down. We're just going to keep getting really, really close to that sum of 8. In this second example, where our ratio was 2, starting at 0, 0, 1, 2, 2, 6, and then 3, 14. We're not really approaching anything here. This is just going on forever. And that's really in part because of this, because our ratio is greater than 2. So probably the most important part of this lesson is understanding that we can only find the sum of an infinite geometric series when the ratio is less than 1 and greater than 0. In this example, when the ratio is greater than 1, the sum does not exist. So the infinite sum does not exist. It goes on forever. This example here on the left, it should be obvious that we're approaching this 8. So the infinite sum approaches 8. And we're going to talk about how you could find that infinite partial sum using a formula in a sec. 2 vocab words you want to be familiar with. When we have an infinite sum that is approaching a value, we say it converges at that number. And so we say it converges at this limit, a limit of 8. And then when the ratio is greater than 1, we say it diverges because the sum does not exist. There's no sum, so we say it's diverging, this infinite geometric series. I think the first couple examples on the homework give you some infinite geometric series, and they ask you, is this series converging or is it diverging? Well, that all depends on the ratio, if it's greater than 1 or less than 1. And instead of plugging this into summation notation, we're going to use the infinite geometric series formula to find these sums. Okay, and the formula is just going to look like this. The sum of an infinite number of terms equals the first term, first term over 1 minus your ratio. Okay, and if we plug that in to that partial sum or that infinite geometric series we did on the left there, you'll see that we'll get 8 for our partial sum there. So let's do that up here. We're going to plug in s sub infinity, our first term of 4, over 1 minus our ratio of 1/2. 4 over 1 minus 1/2 is just 1/2. And then 4 times the reciprocal of 2 over 1 gets us a partial sum of 8. So you can see we're going to be using this formula for the sum of an infinite number of geometric series. Okay, so what I'd like to finish with now is just a couple examples. I'll work out one more together for you guys, and then I'll let you work out 3 or 4 on your own. You can pause the video and work them out and then check the solutions. But let's try one more together. Let's do finding, and the directions on all of these are going to be the same. It's going to be find the sum if it exists. And let's do 5, 4, 3.2, and 2.56, going on forever. Okay, I'll let you guys write that down. First thing we should do is just check and make sure two things. Make sure it's geometric and make sure that the common ratio is less than 1 so we could find that sum. Remember, our way to check to see if we have a common ratio is pick any term and divide by the previous term. So 4/5. Same with 3.2 over 4 or 2.56 over 3.2. They were all going to get you a ratio of 0.8 or just 4/5, same thing. So we can find this sum. And we would just plug it into our infinite geometric series formula. First term is 5. 1 minus your ratio. Our ratio is 0.8. I'm just going to use a fraction because it'll be less work. We don't have to use a calculator here. We get 5 over 1 minus 4/5, which is 1/5. And then we have a complex fraction, a fraction within a fraction. We've done these before where we just multiply by the reciprocal and we get 25. Okay. So why don't I give you guys I'll put 4 more examples down here. And once you're done writing them down, you can pause the video, work through them on your own, and then I'll put the answers up in a sec, okay? So go ahead and write these down. If I'm going too fast, you can just pause the video right when I'm done. Sorry, I lied. I'm going to put one extra example down here. But you'll see it's nice and quick for a really important reason. Okay, when you guys got those written down, why don't you go ahead and work through them. You can hit pause and then unpause when you're ready to check the solutions with me. Okay, so for this first example, hopefully you see in sigma notation, it's an infinite geometric series because 1 to infinity, and then it's geometric because it's 1/3 to a power. It's 1/3 to a power tells you it's geometric. So the sum of this infinite geometric series would be the first term, which we get from plugging 1 in right here. 1 minus 1 is 0. Anything to the power of 0 is 1, so we get 2 for our first term over 1 minus our ratio of -1/3. Be careful with the minus minus. This ends up becoming 1 plus 1/3. So we actually get 2 over 4/3. And then multiply by the reciprocal. 2 times 3/4. We can cross multiply here. And we're just left with 3/2. Okay, for our next example, it's geometric again. The ratio is -1/5 because it's alternating positive, negative, positive, negative. And we plug this into our infinite geometric series formula. 25 is our first term. 1 minus -1/5. Again, this negative negative is going to become positive. So 1 plus 1/5 gets us 6/5. And when you multiply by the reciprocal, you would get 125/6. Okay, for this third example, if you're struggling to find the ratio, remember, pick a term and just divide by the previous term. So 1/2 divided by or times 4/3. You can hopefully see that the ratio here is 2/3. You can check another term if you want. 1/2 times 3/1. Also, 1/3 divided by 1/2, so times 2/1 also gets you 2/3. So the common ratio here is 2/3. Our first term is 3/4. 1 minus 2/3. We get 3/4 over 1/3. And then just multiply by the reciprocal. 3/4 times 3/1 gets us 9/4. Okay, last two. You should have noticed here that it was not a common ratio. There was actually a common difference. The difference was -6. So -6, -6, -6. And right there, if it's not geometric, if it's arithmetic or any other type of series, no sum exists. Okay. Remember, the only time we have a sum for an infinite series is when it's geometric and the ratio is less than 1. So no sum exists for this example. And for our last example, it's geometric because it's some base raised to an exponent, but ratio is greater than 1, which means, again, sum does not exist. Okay, and that's fine. Anytime the ratio is greater than 1 in a geometric series, it's not going to exist. And then if it's any other series that's not geometric, cannot find a sum. It goes on forever. It doesn't approach a number. Okay, there was 5 examples for you there. There's plenty more on your homework. If you guys have questions, our next hangout will be next week, and I'll send out that agenda with what we're doing next week on Sunday. If you have questions, just hold off till then, or you can shoot me an email, and I'll talk to you guys soon.